This is our last lecture in this series. We're going to look at nonconservative mechanical systems. This means paying a little more attention to which matrices are symmetric and antisymmetric. The basic teaching tool will be a robot fisherman. We'll look at its static response and show how static error in positioning occurs. Then we'll look at its dynamic stability, which is equivalent to systems where the gain is turned up and they become unstable in some sense. We'll have a problem session with some 3 more problems. Let's suppose that your assignment as an engineer is to create a mechanical robot to sit on the banks of a stream and fish. You might think about what this would require and what kind of motion would actually catch a fish and pull it out of the water. The structure that we're going to propose is somewhat human looking. In other words, it has something like an arm with a fishing rod at the end of it. Let's consider a very simple model, and it will remind you a little of our fly swatter example earlier. This part of the robot is considered to be either elastic or rigid. We'll ultimately make it rigid before we do any solution, however. The fishing rod is definitely elastic and has a mass and stiffness characteristic. The weight of the fish will be downward on the end of the rod here. I'm going to break the analysis into 2 parts. One is what I call the static response. We're going to put a sensor at the tip of the rod that is going to measure the angle from the horizon, and if the fish pulls it down, then the static idea is for the robot to raise the fishing rod until the tip becomes level. That's somewhat logical because that's sort of what you would do, and you would be able to look out to the end of the rod and decide if it were level or not. Now the amount that it deviates from that is the amount that it has a non-zero slope at the tip, will be considered an error. And that presence then will be what we're interested in on static response. Now when you talk about dynamic instabilities, you mean that is it possible with no load on here at all that the system unloaded will suddenly start to oscillate? That can happen if the control system has its gain, and that is its stiffness and velocity dependent terms, turned up so far that something in the motion of the bare rod allows the phasing in time to be such as to cause a flutter. And it turns out that can happen in this case. The actuator that we use will be rotary, and we'll put a moment in at the base of the rod at the hand of the robot fisherman, basically. And it will adjust that to always try to oppose a rotation at the tip of the rod. In other words, the robot will try to hold the tip horizontal. You see, that would keep the rod from going into the water, for instance, which is what a real fisherman would try to do. We'll use these symbols K and C for the actuator stiffness and damping. I'll use the word damping and velocity dependent interchangeably, so don't worry about that. Then the robot and the rod mass are given matrices with and without the caret, and the robot and the rod stiffness likewise. The weight of the fish, script F, is going to be vertical and positive downward shown here, so it will always be down since it's gravitational, so we'll just take that script F with its own sign convention. We will first assemble the equations of motion and then look at the various matrices involved. We'll comment on what the symmetry or lack thereof of the coefficient matrices means. For physical modeling, we'll use the Euler-Bernoulli beam theory. We'll have motion confined to the xy plane. with no axial force or motion present and no flexure out of the plane nor torsional vibration. At the far wall on the left, there will be no slope nor deflection. V is the relevant lateral deflection of the central axis of the beam. We're not going to look at the weight of the actuator and the rod as loads. The weight, that is, we're neglecting gravity in that regard. Now, they're going to be much less than the fish, hopefully. Anyway, if we catch a big fish. We'll ignore the mass of the actuator and the sensor. Presumably, the sensor is a very small device out at the tip of the rod. We'll ignore structural damping. Now, the things that we're going to keep, you'll see in a minute in the equations of motion. Our finite element modeling now will basically be the choice of the bar element for our two beams in the problem, one representing the robot's arm and the other the flexible rod. Because at the wall to the left we're going to constrain these, it's a rigid wall, we can do that and partition out those two equations. Furthermore, U5 and U3 will be pinned together, so those are identical. And the push and pull in terms of the moments at the actuator here will be equal and opposite through Newton's third law. And that's what the actuator can do, is just put a moment that's opposite in sign on U6 compared with what it puts on U4. We'll make that moment, however, proportionate to the tip rotation shown here and make it oppose that. Now, in the XY coordinate system, Z is out toward us. Positive moments are those that are counterclockwise. This one is clockwise, so it carries a sign minus on it. The desired moment that's applied to the end of the fishing rod at its base is reacted by the robot's arm and in equal and opposite manner. So here's our force on the robot arm. F6 was the live load that we were trying to control the fishing rod with. We need the minus sign for the equal and opposite reaction. So we get that force again as proportionate to both the perceived angular error at the tip as well as the rate of angular error. We consider these moments as external at the present before we build them into the equivalent finite element model. When we form the equations of motion here, and when we first assembled, we put those actuator forces here on the right-hand side as if they were external. The assembled equations of motion are shown here for the 5 remaining degrees of freedom, remembering that we've taken U5 equal to U3 in the case of the translation at the joint, and that's been condensed out. Now, with these degrees of freedom, we get the rod properties such as the rod mass sprinkled around degrees of freedom 3, 6, 7, and 8. And there is no structural damping. And then on the stiffness side here, you get both the robot itself, which is the hatted quantity or the carotid quantity, in this corner, and then you get the beam stiffness out in the degrees of freedom 3, 6, 7, 8 again. On the right you have the true physical reaction F3, and F7 could be the live load of the fish, and then you get the robotic forces here which physically are internal, but we are temporarily treating as external and shown here. Since we want to drive the tip rotation to 0, there is no command angle nor command velocity. We want that to be exactly horizontal. At this point, we'll simplify a little further. We'll set the live load out at the tip to be minus script F, the weight of the fish, because it's downward. And then we move the actuator moments to the left-hand side of the equation. And it's now that we set the robot body to be rigid, which means that we don't have to carry that U3 degree of freedom, nor the U4, because those will both be 0. Then we can partition and bring down this reduced set of equations shown here, which is a 3x3 set of equations. We can already see that the stiffness matrix here is non-symmetric because of the appearance here of the robot stiffness. Likewise, the velocity-dependent term here is non-symmetric. So it looks as if there's some skullduggery afoot here, and this actuator this time might cause us some problems in stability. There's a theorem in matrix algebra that says that you can decompose an arbitrary matrix into the sum of a symmetric and an anti-symmetric matrix. We have obtained two such matrices shown on the left. You don't have to prove this theorem in our case, just see that you can recover the original matrix by adding the symmetric and skew symmetric components that we have given here. The word skew symmetric means the same as anti-symmetric. If you mean that it's a general matrix, once in a while people use the word asymmetric, and that leads to some confusion between asymmetric and anti-symmetric, but the words are unique. They really have meaning. In any event, this symmetric part can be shown in damping problems to cause a dissipative force. This skew symmetric term here, which is on the velocity dependent terms, is gyroscopic. Down here on stiffness, you can show that the symmetric part is a conventional elastic stiffness and stores energy. It's a typical elastic spring. But the one that's skew symmetric over here is what is called circulatory and can lead to a perpetual motion machine. You can either take energy out of the system or put energy in, depending on the various forms of skew symmetry. What I meant by the various forms of skew symmetry is that you can have different signs and magnitudes in that matrix, and then that will determine whether or not it is a energy creator or an energy sink. Let's tabulate some of these ideas here. The symmetric type of velocity-dependent terms can either take energy out or put it in. It's more typically the source of the single degree of freedom instability. It's a kind of flutter that's more of just a single frequency, such as the screech in an amplifier in a public auditorium where the gain is turned up too much and there's positive feedback between the loudspeaker and the speaker's microphone. A common example is just viscous damping. If it's anti-symmetric, then there's no work done by this set of loads, and these are typically gyroscopic or Coriolis forces. But these, although they cannot cause the instability directly, they can affect stability indirectly by the way they unbalance the system in the presence of other non-conservative loads. Symmetric stiffnesses here are the ones that are energy conserving and can store energy, and we think of those as elastic forces. Often if an aerodynamic force is like this, it's considered to be an elastic spring, and so on. The anti-symmetric stiffnesses are the tough ones, They can either put energy in or take it out. They can cause the multiple degree of freedom flutter. They're called circulatory forces. Our first look at a solution will involve the static response of our fisherman robot. The robot attempts to hold zero error measured by this angle at the tip of the rod. The weight of the fish, however, pulls it down. It's a battle between this overturning moment that the fish puts on the rod compared with the stiffness of the actuator, which is trying to rotate it back. This time, fortunately, the actuator is able to sense the local rotation out at this tip, and therefore there is no penalty due to the in the static error due to the flexibility of the rod, because it's definitely trying to correct out here. Watch that as it goes along. It's an amazing thing, and the answer will come out that the stiffness of the rod doesn't matter at all. Having a sensor out there is much more accurate than having a sensor at the root here, but it also leads to instability. When we reduce to a static model, we neglect all the time-dependent terms, but then we keep the beam stiffness terms, the weight of the fish, the stiffness of the actuator, and so on. We'll now look at the reduced static equations. These cover the rotations at both the left and right ends of the flexible fishing rod, as well as the translation at the tip of the rod. So U6 and U8 are the rotations. U7 is the translation of the tip. We non-dimensionalize the translation by dividing by the length of the rod, and then we clear out the various coefficients to end up with this simpler set of equations in a non-dimensional form. So you can see there's one non-dimensional loading parameter here, there's a non-dimensional stiffness parameter here, and non-dimensional displacements there. We could proceed directly to our solution now using Cramer's rule, but instead let's stop a minute and think about dimensional analysis. There is a theorem called the Buckingham PI Theorem that helps a person think from very fundamental reasoning what kinds of variables and how many of them ought to be involved in the problem. Now, we already found an analytical solution where the non-dimensional displacements were functions of a non-dimensional stiffness and a non-dimensional load. Could we have figured that out by other logic from here on down on the Buckingham PI Theorem? And the answer is yes, you could. At least get it in a general form. Our variables in the problem, if we're interested, say, in U8, which is the rotation at the tip, would have been U8, the rod stiffness, this is the actuator stiffness, length of the rod, flexural rigidity of the rod, and the weight of the fish. And then dimensionally, I've put the dimensions under there. Now, this is a static problem. Time doesn't occur. We have 5 physical terms minus 2 fundamental dimensions involved. There could have been as many as 3 mechanical dimensions. The pi theorem says, in general, you ought to have 3 pi terms. And that's what we did get up here, interestingly, at this stage, in the stage of our equation. The pi theorem doesn't really tell you in what way to gather your terms except dimensionally, and these would all be various candidates of weights, stiffnesses, and so we could have chosen any 3 of these. This one we're viewing as a dependent variable, and you would have taken 2 of the others. Now, our equations literally pointed out that you get this one naturally, And this one here we got naturally in just working out analytically. But in principle, you could have gotten these other terms, or any squared or cube of them, had you felt that that was more of a important physical ratio. Now let's return to the analytical solution. I wanted just to give you a taste of what the Buckingham PI Theorem could do. In the continuation of the analytical solution, you have the ratio of determinants. We're solving for the third of those variables in the three equations. So here's our force vector on the right side of the equation appearing in that column. When you turn the crank and simplify this, you find that there's some cancellation, and you find that there's a relation between just two of the three equations, or two of the three terms there. Now that's very unusual, and you wouldn't have expected it. Had we solved for U6 and U7, though, we would have had the three variables all intertwined, but this one came out simpler than we'd expect. And in fact, then you get such a law here that the error U8 is a negative of this loading parameter, so that if the fish is a positive weight fish here, you come down to this point and find that the beam will have a negative slope at the tip of that much. And that makes sense because we've taken script f positive downward, and so we're going to get at the tip of the beam a negative angle, which we call U8. The Buckingham PI Theorem is correct, though, in general, because the other two variables do couple with both of the independent ratios as shown here, if you continue the Kramer rule solution for the other two variables. And so it was only fortuitous that this zero occurred here. And remember, I said at the outset, it was really interesting then that the error out at the tip of the fishing rod here doesn't depend on the stiffness of the fishing rod. That's because the sensor is out there and compensates for whatever droop is in the rod. And you find then that the error here only depends on the moment put on the rod by the fish over the rotary stiffness of the actuator. Well, I thought this was neat, and I thought I would do a little side excursion here and just check the MSC DMAP language to see if it would help us on solving this same set of equations rather than using Kramer's rule. And again, I want to expose you to this in an easy problem because we need this in a few minutes. I took specific values of these physical variables, and then together they imply this, which will occur also in our formulation. And that implies that you would get this result. So we know the result that we should get. But let's go look at the non-dimensional equations that we derived earlier. And here are these non-dimensional equations, and then we're putting in the values that are test values in our case, and then seeing if we get the right results. Now, the DMAP language allows the Nastran user to write their own matrix equations and solve them. I've had to name these various vectors. For instance, this vector is called DISPL for obvious reasons. This one's called loadVec, and I call the portion of the stiffness that was due to the actuator, namely this thing here, with zeros everywhere else, K actuator, and then K rod is the remaining physical stiffnesses there. And assembling these two together, I call them stiff. So we ended up with a very simple algebraic set of equations here with a 3x3 square matrix, and it's nonsymmetric. This figure is full of all kinds of commands for Nastran. I use the solver 100, and you compile this little DMAC program. First, I print out the information that actually is entered later in order to make certain that I've gotten the right rod, servo, stiffnesses, and the right load vector inserted. Then I do the addition to get the two stiffnesses added together into the system stiffness, and I print that out. Then I solve the set of equations. So here's your general equation solver. And then I print out the displacements. The remaining cards below are just reading the data in. Here I'm reading in the rod stiffness, for instance. The first entry here is primarily bookkeeping, telling the rows and columns, and then the remaining ones are reading in the actual data. Next, I read in the actuator stiffness, and it has its own bookkeeping entry and then the actual data. There's only one column there, so it's not hard to handle. Then you also have the load vector with the bookkeeping card, and then the actual vector of data. Then I run the problem, and we print the results out here. You echo out the stiffness matrix. A problem in a sense is that although it's reading out columns, they come out looking like rows, and so you get a bit of an inversion in sense here. The term here is actually K13. It's row 1, column 3. And this is row 2, column 3, row 3, column 3. So if these terms were actually bundled in their normal matrix form, this term here is the one that goes up in the upper right-hand corner here. It's the only unusual term. So watch these little outputs like this because they're sometimes tricky to read. The displacement solution is now printed out, and these are the terms in the vector, and they exactly match the analytical solution. So this shows that our DMAP procedure is correct, gives the same answers as a small analytical solution. I wanted to expose you to that because later we're going to need the DMAP approach for some serious equations, ones which have complex solutions and would be too hard to carry out by hand. Let's look at the stability of this robot fisherman now. Imagine this stream flowing through the beautiful countryside and this robot fisherman pulling in fish, hopefully with a owner that really appreciates them. And now the question is, what if you adjust those stiffnesses in the fisherman's actuator that might cause it to go unstable? Because you'd hate to see this thing having something equivalent to an epileptic seizure out there. Well, we go to the full set of dynamic equations for this, and we zero out what was once a static force in this location. Now the question is, what are the values of the coefficients C and K that might cause dynamic or even monotonic divergence as forms of instability? This is similar to other stability studies for the homogeneous differential equations. You look for harmonic solutions and decide whether or not the time dependence makes it grow in time or subside in time. First, let's put this in a non-dimensional form. We'll assume harmonic motion here with e to the pt behavior. Then we put in the physical beam stiffnesses and masses. I'm willing to use consistent mass for a little better accuracy here. On the right, I have a non-dimensional displacement at the tip, phi7. Note that the frequency term, p squared, appears in every one of these components. It occurs also to the first power in this term here, which we recognize as a pseudo-damping term. Let's pause at this moment and take a look at Buckingham Pi analysis again to see if we're somewhat in the right ballpark. We have dependent variables in the problem of the frequency of oscillation, or at least a frequency parameter, and then the various mode shapes that might occur. I'm going to give the mode shape a specific pi number, pi 2, thinking ahead a bit. These are physical quantities here. This is running mass per length of the beam. This is the flexural rigidity. And then we have the total length of the beam, the actuator stiffness, and the actuator velocity dependent term. If we forget about the mode shapes for now, let's think about P here as a function of these other 5 quantities. It turns out there are 6 variables involving 3 dimensions, and therefore Buckingham Pi would say that there ought to be 3 independent terms here, that we ought to have pi 1 perhaps depending on a pi 3 and a pi 4. Later, if we want to solve for the dependent variable pi 2, we could make it depend on pi 3 and pi 4 as well. These non-dimensional ratios have been suggested by what we see in the analytical solution. There is a little bit of complication on this term. It's a little bit hard to figure out, and it's only through skullduggery that we're able to identify how to do this particular damping term. We can now write the non-dimensional form of the equations by using these pi terms. Here's the algebraic form of our equations of motion, where the harmonic assumption has led to these frequency terms sprinkled throughout the equation. This pi 1, as you remember, is a function of the frequency parameter p squared. By careful choice of this velocity-dependent term here, which many people think of as a damping term, it frees us to pull out the frequency dependence here as the square root of pi 1. For this set of equations to have a non-trivial solution in these eigenvector components, we must have the determinant of the coefficients to be 0. Because the pi 1 is squared in p, the characteristic polynomial will be a 6th degree polynomial. The robotic stiffness occurs in this pi term, pi 3. So we've got robotic stiffness here, we've got robotic damping here. Writing this out in a form that's a little easier to see here, but just as a set of equations that depend first of all on the square of frequency and then the first power of frequency, and then this term here, which is frequency independent. You have the following equation. I'm now using pi 2 as the non-dimensional eigenvector set of terms. The characteristic equation itself, which is the determinant of these coefficients to be 0, does not involve pi 2. It only involves pi 1, the frequency term, as a function of the robot stiffness and the robot damping terms. Our motion, of course, depends, like e to the pt, shown here, and the stability depends on the real part of p. The real part is the envelope of the oscillation, And if it's positive, then you get a growing oscillation in time. If it's negative, you get a subsiding oscillation. Pi1 is our frequency parameter. It does involve the stiffness of the fishing rod as well. The eigenvalue that we're really interested in, though, is the square root of pi1, so that we get it only in terms of the frequency's real and imaginary part, and not the square of that as shown up above. Taking the square root of these physical parameters doesn't affect things because those are always real positive numbers. Well, let's do a DMAP solution now. This problem is too difficult for us to solve by hand. The stability polynomial, the so-called characteristic equation, is a 6th degree polynomial. We will have to cut out the damping from the actuator in order to make it manageable, and we don't have any external forces such as the fish. We're going to solve this problem rather thoroughly, where the frequency is a function of the actuator stiffness. Of course, all in suitable non-dimensional ratios. And then we'll present the results in the figure of the square root of pi1 imaginary versus pi3. This will be the frequency part, and we will comment on the stability as it varies along those curves. I'm going to write a DMAP program for specific values of the parameter pi3. We'll take the example of pi3 equals 3. Again, I use Sol 100, and we compile the DMAP. We print out the various stiffnesses. Again, we have the fishing rod stiffness, K-rod, and the servo stiffness. We add the two stiffnesses to get the system stiffness, and then print it out. Then this is our complex